class. Okay. Inert pair effect. Actually, when we have some electrons, okay, generally in S subshells, okay, like in boron, in carbon, in nitrogen families we are talking about, okay, they actually do not participate in the bond formation. They are not participating. The S electrons, they are not participating in the bond formation due to sudden increase in the nuclear charge, okay, and this generally results in the, and this incident in which actually the S pairs of electrons are not participating, okay, they are considered to be as, means actually they are present but they are not participating in the bond formation, okay. So this effect is known as inert pair effect, okay. Let me write the definition first, okay. Electrons pair of electron pair of NS subshell, NS subshells we are talking about, NS subshells, last member of boron family, either it is boron, last member of boron, carbon or nitrogen family, okay. Nitrogen family you are talking about, nitrogen family, okay. Actually they can't participate in the bond formation, means they can't participate in bond formation, okay. Due to why they don't, because there is a sudden increase in the nuclear charge, effective nuclear charge, okay. Due to sudden increase in effective nuclear charge, okay. And this phenomena is known as inert pair. Inert, not participating, pair means pair of electron, we are talking about electron pair effect, okay. So what is this actually? For example, let if I'm having boron, okay, here boron is going to have 1s2, 2s2. What is the atomic number of boron? Hydrogen, helium, lithium, beryllium, boron, 5. Okay. So it is going to have 1s2, 2s2, 2p1. Okay. Now you know that here if we have this 1s electron, this is 2s2 and this is 2p1. Okay. 2p1. But sometimes you see here that the boron, if it is going to have one electron, it can jump into this one. Okay. If it is going to have valency 1, like p orbit, so boron valency will be considered as +1, and here it's, if it jumps to this one, this is the second shell, and this is also second shell, 2p, this is inner shell. So the electron of this one is not going to participate, but this electron can participate. So if it jumps into this one, so when it jumps into this one, so there will be in excited state, it will be going to have one electron in this one and 2 electron in this one. Okay. This one, the 1 electron from this one jumps into this one. So it will become 2s1 and 2p2. And there is this is going to have 3 unpaired electron and it will be considered as +3. Okay. You understood?
Yes, sir.
But here you know that boron is going to have +3. This is simple. Okay. And if we have carbon, like if we have carbon, carbon valency is 4. You are very much familiar. This is boron. The boron has valency 1, and when it is going to excited state, then it is going to have +3. Now, if I'm talking about this is carbon, carbon has valency 2 and 4. So +4, right here, 3 here. Okay, right, 2, most possible. 3 and then yeah, 1 here. Okay, this is +4 and 2. How to? 1s2, 2s2, 2p4. Okay, that total, sorry, 2p2, 1s2, 2s2, 2p2. Okay, so we have this electrons here, like this. Okay, and 1, 2 here. So when it jumps to this one, so it will become, otherwise, if in the ground state, it is going to have +2 oxidation state. Okay, +2. But if this electron goes to this one, then there will be 4 unpaired electrons. So in excited state, it is going to have, okay. So this is known as +4. Okay, you understood this one?
Yes, sir.
Similarly, nitrogen also. Nitrogen has +5 valency and +3 valency. So in case of nitrogens, generally we have 1s2, 2s2, 2p3. Okay, then it is going to have 3 unpaired electrons. And sometimes it's these two inner electron, they are all going to participate. So it is going to have +5 also, like N2O5. Okay, nitrogen is going to have 5 valency. So in many cases, nitrogen is going to have +5 and +3 valency. Okay, you understood? But as we go down the group, like boron, if it comes down the group, like aluminium, gallium, indium. Okay, and similarly, if I talk about this carbon, okay, if I talk about this silicon, germanium, and tin. Okay, and nitrogen like phosphorus, arsenic, antimony. Okay, and Sb. So if I'm talking about this all elements, so as we move down the group, the tendency of inert means they all are going to have ns2 electrons and np2. Okay, ns2 and np2 electrons. But here, like in the carbon, they are just going to have, we means the inert pair of electrons means these are participating here. 1s2, then 2s2, and then 2p2. So this electron will jump to this one. But as we go down the group, due to sudden increase in the effective nuclear charge, these electrons do not participate. The tin has two possible valencies, which is going to have +2, +2, and +4, +2 and +4. But more acceptable is this one, means more advanced, or we can say that the tin which is going to have, means which valency tin is going to make bond. This is +2, not +4. Why? Because here ns2 and np2, these electrons are not participating in the bonding because this is due to sudden increase in effective nuclear charge. And why this sudden increase in the effective nuclear charge? Because of the poor shielding effect of f orbitals. Because as we go down the group, the f orbital electrons comes in the nucleus. Okay, this is due to add an extra 14 electrons, and f orbitals are not able to shield. They have f orbitals, electrons are going to have poor shielding effect. F orbital electrons have poor shielding effect, and as a result of which they are not able to, the nucleus become more powerful, because they, as you know, that number of electrons are added, then the number of protons are also added. So due to addition of 14 proton, but poor shielding of f orbital electrons. So here is f orbital electrons, and they are not able to means they are not able to shield the effective nuclear force of this one, means they are not creating a barrier. So for if here is ns2 electron, due to special attraction of this nucleus of this electrons, okay, by this nucleus, because of extra 14 electrons by the f orbitals, these electrons do not participate. Only the p electrons are going to participate. Okay, you understood? Here is p
Yes.
and p electrons, and here is n ns2. So these electrons do not participate. This is because of the increase in effective nuclear force. Why? Because the 14 electrons are added due to f orbitals. 14 protons are added due to f orbitals, and moreover, here we have, okay, moreover, if due to, and if f orbital is able to shield properly, then this nucleus force will not be able to reach to this one, they can participate. But due to increase in 14 electron by the f orbital and poor shielding of f electrons, f shell do not shield, means it is not going to shield it properly. So the nucleus will be visible to these electron. Nucleus will be visible, okay, visible to ns2 electrons, will be visible to ns2 electrons, as a result of which we can say that these electrons, due to increase in positive charge, they are not participating in the bonding. You understood? You understood?
Yes, sir.
So here we can say, as we move down the group, due to increase in positive charge, like this, ns2 np1, ns2 np1, here is ns2 np2, and here is ns2 np3, np3. Okay, as we go down the group, the 32 electrons are added, and we can say that out of 32 electrons, 14 electrons, means as we go down the group, as a next shell we are adding, okay, the 32 electrons are added. Okay, and as we keep on adding the out of 32 electrons that are being added, okay, the 32 electrons that are being added, out of this 14 electrons belongs to the inner 4f subshell. Okay, means out of 32 electrons, as we move down the group, the 32 electrons are added. Okay, so out of 32, 14 electrons enters into 4f subshell. Okay, subshell, and as a result, and therefore poor shielding occurs. Okay, therefore poor shielding 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 observed. Okay, okay, poor shielding is observed. As a result, as a result, the effective nuclear force increases. Okay, done.
Yes, sir.
So what are the factors, or what are the things that are being affected due to inert pairs? So we are going to write here, due to inner pair effect. Due to inner pair effect, we can say that, first of all, the stability of lowest oxidation state increases from top to bottom. So for example, if I'm saying that tin has +2 and +4 oxidation state, and carbon has +4 and +2 oxidation state, because carbon is above. So here the effective nuclear force is not, because not so much, or we can say that there is no f orbitals present here. F orbitals electrons are present here. So here in this case of carbon, here the +4 oxidation state is more stable. Okay, but as we go down the group, then here +2 oxidation state, because of this one, the ns2 electrons are not participating. That's why we'll say here that uh, this +2 oxidation state will be more stable. Understood?
Yes, sir.
So here we can write it that, first of all, in beryllium, boron, we have 3 oxidation state, then aluminum +3 is stable, then gallium +3 is stable, then indium we have +3, and means +3 oxidation state. If I take the order of this +3, so boron will be the first in the stability of this +3 oxidation state, and then tellurium +3. And if we talk about this carbon, +4 oxidation state is stable in carbon, then silicon then silicon, then we have germanium. Okay, +4, then tin, and then Pb. Okay,
Yes, sir.
noted this one.
Yes.
Okay, next, stability of lowest oxidation state. Lowest oxidation state increases from what we have written here. Stability of lowest oxidation increases from top to bottom. They indirectly they're the same things. Okay, don't write it. Next is, if I talk about the another one is the element with highest oxidation state with reduce and act as an oxidizing agent, means which is going to have the highest oxidation state, they act as a reducing agent. Sorry, oxidizing agent. Okay, they act as an oxidizing agent. So for example, if this is an important part, okay, you need to understood this one. For example, if you have gallium is +3 going to have +3 oxidation state, and it will lose 2 electron more easily. Okay, are you getting my point? If it is
Yes, sir.
gallium, okay, it will lose 2 electrons more easily and will comes to the, sorry, it will gain 2 electrons and will, I mean, after gaining the 2 electron, it will acquire a positive 1 charge. Okay, why why
Because there's only one.
Yeah, they are stable at 1. Similarly, if we have tin, which is going to have +4 oxidation state, so it will acquire 2 electron. If you give it 2 electron, then it will become tin 2 positive. Tin 2 positive. Why tin 2 positive it is becoming? Why? Because this is more stable, or we can more stable, or this is less stable. Less stable. Okay. So actually they are helping, means they are gaining the electron to itself. Addition of electron is called reduction. Okay, so here a reduction is taking place, and those substances that are oxidized, sorry, that are reduced, is called oxidizing agent. So it is acting as an oxidizing agent. Okay, got it. This is
Yes, sir.
important, that gallium 10 can easily means add the electron to itself, because in order to change their oxidation state from higher to lower. So note it down that element with higher oxidation state, element with higher oxidation state act as oxidizing agent. Okay, got it. Note this one fast.
Done, sir.
Okay. Here we have, next is boron and carbon. Like we're talking about boron and carbon and nitrogen family. Okay, we can say that the members which are at the top, they are stable at the highest oxidation state, and the members which are at the low, means lower of the, or we can say that these are at the bottom of the periodic table, are stable at the lowest oxidation state. Okay, okay.
Yes, sir.
Okay, and similarly, note it down, element with lowest oxidation state, for example, element with lowest oxidation state like tin 2 positive, okay, will act as an oxidizing agent, or reducing agent, will act as oxidizing agent. Why? If they, like what example, this one, they are acting as an oxidizing agent. Got it? So if you are talking about the bottoms elements, the bottoms element will act, they will easily gain 2 electrons, like it will gain 2 electrons and will form, sorry, from tin 4 positive, it will gain 2 electrons and will become tin 2 positive. Okay, because this is more stable. Okay, Like if we're talking about the carbon, in carbon, if it is at 2 positive, okay, then it will lose 2 more electron and will form carbon 4 and here. So at the top of the elements which are at the top, they will try to lose the electrons, and if they lose the electron, what the oxidation is taking place. Here the oxidation is taking place. If carbon, why carbon is losing 2 electron? Because it is more stable. Carbon 4 is more stable. Okay, more stable. And here it is actually from plus 2 to it is going to plus 4. Why? Because it is more stable and it is less stable. Less stable. But in case of 10, if I talk about this one, here the reduction is taking place. Reduction is taking place. So it will act as, if reduction is taking place, sometimes someone is getting reduced and it is getting reduced, then it is acting as an oxidizing agent. Oxidizing agent. And here oxidation is taking place, then it is acting as reducing agent. Reducing agent. Okay, so we can simply say that the element with lowest oxidation state will oxidize and act as reducing agent. Okay, got it? Element
Yes, sir.
with lowest oxidation state will oxidize and act as reducing agent. And we are talking about this one at the top of okay, top of the element we are talking about. Okay, if like if I'm talking boron is +1, then it will easily go to boron 3 positive. Okay, why? Because it is more stable, so it will lose 2 electrons. So here it is getting oxidized, so it will act as an reducing agent. Okay, reducing agent. You got it? So if
Yes,
an
sir.
element is going to have +2 oxidation state, the simple is, if it is for example, if carbon is already at +4 oxidation state, so it will not go to +2. Why? Why? Because it is already stable. Already stable. It will not gain 2 electron to give C2 positive. Why? Because it is already stable. So if I'm talking about this one, if the element is going to have if the element is going to have +4 oxidation state or higher oxidation state. Okay. So in case of tin, this will go to tin 2 positive because it is more stable. More stable. So if the element is getting addition of electron, is called reduction. So if the element is added or and a substance is getting reduced, so it is acting as an reducing agent. Okay, so we can simply say here is that if the element is at higher oxidation state, and if it is automatically getting the 2 electron, if it is possible, if it is getting 2 electron and getting reduced, then it is considered to be as an oxidizing state. So if those elements that are at higher oxidation state, they act as oxidizing agent, and those elements that are at lower oxidation state,
They act as reducing agents.
My laptop got stuck. Just a minute. Is my voice is audible to you, Noah?
Yes, sir.
Okay, so what we are just going to study here is that boron, nitrogen, and carbon families. Okay, the members with lower oxidation uh, state. Okay, are at the means the member with lower oxidation state are stable means are present at the top or the bottom. Tell me. The members means that support or that wants the lower oxidation state, they are present at the lower or at the top.
They're present lower.
They are present in the lower. Yes. Okay. Now here we have a question. Okay. Which of the following species is highly stable? Okay. Which of the following species is highly stable? Okay. Option A is XS2. The option B is SIX2. Option C is SNX2. Option D is PBX2. Tell me. Hmm? Which one do you think is more stable? Uh-huh.
Option A.
This is the way that we have. Hmm? You know that as we go down the group, the +2 oxidation state is more stable. So this one will be more stable, okay? Because XS2 means that it is going to have +2 valency, it is going to have +2, this is going to have +2, this is going to have +2. So all of them are going to have +2 valency. So as a result of which, you can simply say that 2 +2 will be more stable as we go down the group. Okay. Got it?
Okay. Yes.
If I talk about that, which of the following species is full oxidizing agent? Which of the following, let's take the next slide. Which of the following species is powerful oxidizing agent? Is powerful oxidizing agent. Okay. Agent. A, Ba3 positive. B option is Al3 positive. C option is, and D option is tellurium 3 positive. Here we have written gallium. No? This is Ga. Tell me. Which one is more oxidizing agent? Powerful oxidizing agent. Oxidizing means that is itself get reduced. Okay. So we have boron can have +3 oxidation state. and tellurium is also having +3 oxidation state, and this can have +1 oxidation state also, +1, and this one can have +1 oxidation state also. So do you think that which one is a strong or powerful oxidizing agent? Here the oxidizing agent means that addition of electron is taking place, because if it is itself getting reduced, then it is considered to be as oxidizing agent. Okay, you understand
Yes.
this one? Then tell me fast. Tell me. So as we go to this is bangan. Bangan. Do you know Hindi?
Yes, sir.
Bangan, aloo, gajar in thela. Okay, TL. So you know here at the top the +3 oxidation state will be more powerful, and here at the bottom +1 oxidation state will be more powerful. Okay, will be matlab more stable. So as we go, this is +3 is more stable than +3. So if I talk about that in which one the +1 oxidation state will be more powerful, then this is going to have the tellurium is going to have the most powerful oxidation state. You understood?
Yes, sir.
Now, how if tellurium is going to have here, tellurium is going to have +3 oxidation state, then it will acquire 2 electron to give or add 2 electron to give +1 oxidation state. Okay, now addition of electron is called reduction. You can say that this is +3 and it has reaches to +1. So reduce or reduction, reduction in oxidation state, reduction or decrease or decrease in oxidation state, in oxidation state. Okay, reduction or decrease in oxidation state is called reduction. Okay, it's called reduction. So you can simply here the oxidation state is being reduced from +3 to +2, so this is called reduction, and the substance means this is reduction is taking place, this is reduction is taking place here. Substance that is going to be reduced is considered to be as oxidizing agent. This is oxidizing agent. Oxidizing agent. Now you understood this one?
Yes, sir.
Okay. Next question for you. Have you noted? Noted, please.
Yes, I noted.
Are you making the proper notes? Sure. I don't think that you are,
Yes.
because instead I instantly stop writing and you said that I have written this one. So how it is possible? It will always take 1 or 2 minutes to copy your piece and everything. How fast you can write it? So are you sure or are you taking the screenshot?
Sir, I'm writing the notes.
You're writing the notes. So should I check it after the class?
Okay, sir.
Which of the following species is a powerful reducing agent? Is a powerful Here we have A is C2 positive, B is Si2 positive, C is 2 positive, and fourth is Pb2 positive. Which one is more powerful?
Carbon 2 positive.
Yes. Reducing agent means that when it is getting oxidized by losing 2 electrons, then here oxidation is taking place. And since oxidation is taking place, so this is considered to be as reducing agent. And if it is a reducing agent, and why only carbon? Why not the other? Because in this one, this is more stable oxidation state. Okay, understood?
Yes, sir.
Okay. If I talk about this one, that question that is sometimes been asked in the NEET or JEE exams. So number of ions in TLI3 is A option, 2, B option, 3, C option, 4, D option, 1. Number of ions in TLI3. Hmm?
3.
D. Actually, you know that tellurium is going to have +3 oxidation state and tellurium can have plus
Plus
one
1.
oxidation, plus one oxidation state. Which one is more stable?
Plus 3.
No, as we go down the group, the lower oxidation state. Tellurium is at the bottom. Okay.
Okay.
Here it is bottom. Okay. So if it is in bottom though, this one will be more stable. Okay. Plus one oxidation will be more stable. Now you know that if tellurium is going to have plus one oxidation state, okay, then this I3 will be acting as -1. Okay. If it is more stable, then there will be 3 minus I minus I minus I. Okay. These three will be forming -3 and TL3 positive. Okay. So if tellurium is going to have +3 oxidation state as more powerful, okay, like if I'm talking about instead of tellurium, if I take AlI3, AlI3, Al I3. So here aluminum is going to have +3 oxidation state, more stable +3. And this one iodine, then there will be must be 3 iodine like Al -1, -1, -1, and this is +3. So there are 4 ions present here. Okay, there are 4 ions. 4 ions. But if tellurium is going to have +1 oxidation state, then this I3 will be acting as -1 or as a whole. Okay, so there will be only 2 ions. Okay, so don't make it like this way. Make it like means it does not dissociate like this. It dissociate like this. Okay, tellurium +3 if you are taking, then it will be I minus I minus I minus. No, it is incorrect. Okay, this one is I minus. This one is incorrect. Which one is correct? Tellurium +1 and I3 -1. This is correct. Understood?
Yes, sir.
So now we have finished this chapter. So may I know that which chapter would you like to start today?
Uh, Structure of atom.
Structure of atom. Okay, structure of atom. Let's start the structure of atom. Just let me start. Let me have a new slide for it. Structure of atom. Okay. Structure of atom. Okay. Keep revising these topics that we have studied. Otherwise, this will create a problem. Okay. So if I talk about the structure of atom, Okay. So if you talk about the atomic structure, so you know that atom is the smallest individual particle which has three subatomic particles. Okay, electron, proton, and neutron, and they are the masses of electrons, proton, and neutrons. And you know that the total mass of the atom, okay, is concentrated in the nucleus. Okay, then a neutron plus proton constitute total mass. Total mass of atoms. Okay, and you have this studied this one in also in the ninth standard. Okay, got it. So electron, proton, and neutron is actually the we can consider that these are the three subatomic particles, and we are just going to study that there are certain experiment that was done in order to for the discovery of electron, proton, and neutrons. Okay, so the very famous experiment that was done by J. Thomson. Okay, that was cathode ray experiment. Okay, so if I talk about this one, the basics of discovery, discovery of subatomic particles, subatomic particles. Okay, the first one is cathode ray experiment. Cathode ray experiment. Okay, the first one was this was done by J. Thomson. Okay, J. Thomson does the experiment in the discovery of electron. Okay, the second one was means this experiment was done by J. Thomson, and what was discovered? What was discovered? Tell me. Electron was discovered. Electron was discovered. Okay, the next one is, if I talk about next one is positive anode ray experiment. Anode ray experiment. In the anode ray experiment, which was who did the anode ray experiment? Tell me. Who did the anode ray experiment? Are they no?
Yes, sir.
Gold Einstein. Okay. And what was discovered? Proton was discovered. Discovered. Okay. Next one is, and if I talk about this one is, there was an experiment done for the neutral mass of this one. That means beryllium, which is going to have mass 9, and this one. When an alpha particles is added to this one, okay, O2, then it will give carbon 12 plus 1 neutron, 1 neutron. Okay, and this experiment was done by Chadwick, and here proton was discovered. Proton was discovered. Okay. Okay, note it down, please.
Done, sir.
Okay. That's so here is something that we studied about this one. Okay. That electron, proton, and neutron was discovered and how they were discovered. So there's something that you have studied this one in the books also. Let's start with this one. Or should I explain you the cathode ray or anode ray experiment also? Hmm?
Yes, sir.
Should I teach you that one?
Yes.
Okay. So just a minute. Give me a let me put up the slides here. Yes. Okay, let me teach you why. Actually, how the electron and proton was discovered, let's discuss. There was a scientist named as J.J. Thomson, okay, who did some experiment, and when he was doing some experiment, he was doing cathode ray experiment, okay. What he find here is that there was some charged particles, okay. He made this tube-like structure. This is known as cathode ray tube, okay. And this one, and here is some zinc sulfide screen present. Here is zinc sulfide screen that is present here. And what is the role of this zinc sulfide screen? ZNS. What is the role of this zinc sulfide screen? Actually, this zinc sulfide screen is actually this. We can say that when the charged particle strike over it, it glitters. It glitters. Okay. And this is the structure, basic structures of this one. Negative, positive. Here and almost here is a vacuum pump. Okay. We can consider this one as vacuum pump or vacuum pump, which actually eject out this one. Okay. Which eject out this whole air from this almost all the airs, and it was having a pressure of 0.011 mm Hg, which was very less. Okay, so almost all the air was removed. Okay, so very low pressure is there, very low pressure, at very low pressure. Okay, very low pressure is there, and when electricity or when high voltage is passed through it, high voltage, high voltage up to 10,000 volt. Okay, 10,000 volt is passed through it. Then he observed that there are some charged particles, okay, that are moving from negatively charged rod towards the positively charged rod. Okay, they are moving from negatively charged rod towards the positively charged. Got it? That there are
Yes.
something that are moving when very low pressure, means almost all the airs has been removed from this tube, and when we pass the high voltage current to it, then we find that there are some particles, there are some beams that are passing from negative to positive terminals. Okay, and how he discovered that this is a charged particle beam? There are so many ways. What were the characteristics of this one? That when we are just having a flying wheel here, okay, when we are having a flying wheel here, okay, if we put the flying wheel in this one, then this flying wheel start rotating, and this flying wheel start rotating, it is start rotating. Okay, so it means that these charged particles have some mass, means it means these charged particles charged particles is having mass and kinetic energy. Okay, because they are just moving. So moving means, for example, you know that if this is a stationary something, okay, this is some stationary things, and if it start rotating, then it is only possible then if some charge particle hit this, sorry, if some mass particle hit this one, and it transfer its momentum to this one. Okay, for example, if a moving particle hit this one, then some of the kinetic energy of this one will be transferred into this one, and they will start moving. Okay, so kinetic energy is formula half mv square. Okay, then there must be mass and velocity. If any one thing is zero, then it is not going to have kinetic energy. So moving energy means kinetic energy. So we can say that these charged particles are having kinetic energy, momentum. Okay, momentum means why momentum? Because if this is a car, okay, this is a stationary car here, and if some car hit the other, or we can have a football here, okay. So this is a football, okay, this is a football, okay, and if you hit it, with something, and this football start moving and rolling on this grass, or the land. Why? Because you have transferred your momentum to this one. This movement of this ball is only possible if you transfer the momentum. And if the momentum is being transferred, it means this momentum is only being transferred if an object is going already having some momentum. So momentum can be transferred from one object to another object, okay, just by, okay, you understood this one?
Yes, sir.
Okay, so this is called the transformation of momentum. The momentum is only transferred when already something is having. So first of all, they can rotate the flying wheel. Moreover, if you put instead of this one, if you put a something, if you put, okay, like if you put an heavy mass object here, or heavy metal plate, heavy heavy metal plate, then it will produce some rays which is called X-rays. Okay, so this means that this particle, and it can heat it. It can heat if you put a heavy metal plate, then it can heat it. So it means heating means something. It is also going to have potential energy. It is means heating. Heating is only possible if the particles are going to have potential energy. So we can say that these particles are going to have potential energy. Moreover, the important and very important thing is that how can you recognize that these are the charged particle? These are the beam of charged particle. How can you recognize this one that these are the beams of charged particle only? They may be the beam of non-charged particle, like in lights, laser light. These are laser light is a beam of non-charged particle. Okay. Okay. So what is the proof of this one that these are the beams of charged particles? So when you bring a magnetic field, okay, magnetic field nearer to these charged particles, okay, when you bring magnetic field nearer to these charged particle, then these charged particle in the presence of magnetic field, okay, if electron is moving to this direction, then okay, then the current direction will be considered as opposite to this one. Okay, so as you know that charge particles, moving charge particle behave as a magnet. Moving charge particles behave like a magnet. Are you getting this one? Moving charge particle
Yes,
behave
sir.
like a magnet. Okay, so if the charge particles are moving, then they will behave like a magnet. And a magnet exert a force on another magnet. For example, if you have this magnet, North Pole and South Pole, okay? And another magnet, if you bring South Pole and North Pole, so they will attract each other, okay?
No.
And if you bring these same poles, they will repel each other. They will repel each other. So similarly, these moving charge particles behave like a magnet, and if you bring a magnetic field here, so either they will be attracted towards these magnetic poles, or they will be reflected, or they will be divert from these poles. Okay, so in the presence of magnetic field, they are being attracted or repelled towards the, okay, this, if this is North Pole, this is South Pole. Okay, so they will be attracted like this, they will be moving like this. You understood?
Yes, sir.
And this is the only proof that these beams are of charged particle, because if you are having a non-charged particle beam, light beam, if you are having a non-charged particle light beam, like the laser lights, laser beam, so it is non-charged particle. Laser beam is non-charged particles beam, and if you bring North Pole and South Pole a magnetic field near it, they will not get deflected, because non-charged particle do not behave like a magnet. Okay, because non-charged particle do not behave like a magnet. Okay. So if the non-charged particle, like the photon is a particle of light. Okay. So if it is moving, so it do not behave like a magnet, because photon is not a charged particle. Only electron is a charged particle, proton is a charged particle, Alpha particle is a charged particle. So if they are moving, then they behave like a magnet. Okay. And a magnet can exert a force on another magnet. Are you getting my point?
Yes, sir.
Next is, next is that the first point was that if the magnetic field is, first of all, this experiment was done by J.J. Thomson. When we are just going to have a very less amount of air, a very low pressure inside this one, and we when we pass the high voltage current to it, then we find that from negative to positive terminals, okay, these charged particles start moving. And this is the proof that if the charged particle is moving from negative to positive, okay, this means that only the negatively charged particle can move from negative to positive. Positively charged particle cannot move from positive to from negative to positive, okay? Because positive repel each other. So this is the only negatively charged particle that are moving. So it proves that there are some charged particles that are present in the atom, and they are moving from negative to positive terminals. Okay, got it?
Yes, sir.
Similarly, if you bring an electrostatic field, okay, and if you or electric field nearer to these electrodes, okay, to these electrodes, if you bring electric field to these electrodes, okay, then they are also diverted. They are also diverted in the presence of this electric field. If you bring an electric field, positive and negative here. So we will find that they move towards the positive terminals. They move towards the positive terminals when the electric field is applied. Okay, so indicating that these are the negatively charged particles. They are the negatively charged particles. Okay, got it?
Yes, sir.
So let me show you this experiment on the in video so that it will help you. Then we shall be discussing further part of this one. Okay, just a minute.